take this with me. All right, so I'm Paul Bruffett. I am a big data and analytics architect. Really, I guess not I am the architect at Devon. So a lot of my job revolves around supporting our data science team. It works for Kathy Ball and taking the sort of algorithms and the models that they develop and instantiating them, right? So we are right now doing a whole lot of work in Azure. We've had a Hadoop cluster for some years now, and we're taking that, we're moving it all to the cloud, so that's a lot of my day job right now. But at the same time, we're trying to introduce new technologies and empower our teams with some of these new technologies. One of those is deep learning, specifically using TensorFlow and Keras. So we have some use cases at Devon that we're exploring with it, some of which have been successful, some of which have been less successful, right? And I can talk a little bit about some of those. I guess a little bit else about me. I adjunct at OU, so I've taught Python and cloud graduate level courses for some years now. So I've got some familiarity with that. Big Python advocate, so a lot of the work that I do and that our team does is in Python because I make them. So anyway, that's about me. What I'm going to talk about is I'm going to talk a little bit, I think I have a grab bag for everybody, right? So I'm going to talk a little bit about some definitions, what neural nets are, and then I'm going to actually go into some of the different architectures, some of the problems that they solve, and then we're going to look at just at kind of how we train them, and then a little bit at TensorFlow and Keras, and then talk about some of the challenges with both of those. If you got questions, you can ask. Otherwise, I'll try to save time at the beginning. All right, so let's talk a little bit about some definitions. So this slide is from NVIDIA. So if you're not familiar with it, NVIDIA is kind of dominant in this space right now because GPUs have proven to be a breakthrough for deep learning, and that is because GPUs are exceptionally good at doing massively parallel linear algebra calculations, which at the end of the day, that's all deep learning really is it's a bunch of linear algebra that you perform on all your weights, on all your layers across the network, which we're going to talk about in a lot more detail. But with some of the modern NVIDIA GPUs, you get several orders of magnitude performance improvement, talking like 20x performance improvement over doing it on the latest Intel chips, right? So NVIDIA is big in this space. That's why we care what they have to say about it. So the way that they kind of define these layers, and what I'm really talking about is deep learning over here. They talk about artificial intelligence, so you know the machines that would play chess or were the AI in video games, things like that, right? Artificial intelligence, usually things like decision trees. They're talking about that. That's been around for a while, right? Then machine learning kind of came around, and the way we describe machine learning generally is just automated algorithm generation, which means we're doing things like decision trees or random forests or linear regression models that the computer has taken the data and the computer has learned from the data, right? We didn't program it, we didn't tell it how to make the decision tree, we just set up the parameters around it. We've had machine learning for some time as well. And deep learning and AI have actually been around for a long time too. A lot of the sort of seminal papers on it are actually from the 80s. It's just that we didn't have the power to really realize the promise or the hope for these networks until recently. NVIDIA is saying about the 2010s, and that's kind of when I think it was Google really started popularizing the use of GPUs for deep learning. And kind of now we've had these huge breakthroughs and huge rapid improvements. So deep learning, as I define it, as NVIDIA defines it, involves artificial neural networks. So what is an artificial neural network? It's roughly inspired by the human brain's interconnected neurons. So we have layers of interconnected cells, and these cells do calculations, and then they're connected to each other with weights, which also form sort of a calculation. What we do is we feed millions of examples into the network to teach it to recognize patterns. So artificial neural networks are really good with big data problems. Whenever you have 500 records that you're trying to train on, it's probably not a good artificial neural network problem, right? If you have even in the thousands, low thousands, it's usually not a good artificial neural network problem, unless if you're talking images or unstructured data like videos, then it's probably still pretty good. So anyway, we feed those in, and we'll talk a little bit about the training process here in a minute. And eventually the network tunes, right? And it starts to recognize patterns within that data that you've fed it. So deep neural networks can extract high-level features from the raw inputs. We'll see an example of that with a convolutional neural network here in a minute. They automatically learn abstract representations by continuously tuning and optimizing neuron weights. All right, so this is going to make a little more sense as we come back to it. So I'll talk about how they work in a more detailed slide here in a second. But I talked about what they were good at and what they weren't good at. And so based on, we need lots of data, like I just said, right? Hundreds of thousands of samples is really kind of where they start to come into their own for structured data. For unstructured data, you can do it with thousands, like pictures. Mini features, that's also really powerful, right? So, so one of the use cases that Google has is obviously very sparse data, right, around customers that use in a different variety of their services or making a variety of searches. It becomes a very sparse, very wide matrix, right? That's why they use Bigtable for some of that. And so artificial neural networks are pretty good at that because they can do sparse data representations in a better way that traditional machine learning solutions might be able to. Images or videos, so this is really powerful. This is kind of the breakthrough, right? It is really difficult to do image or video classification with traditional methodologies. Artificial neural networks make this fairly trivial with a labeled data set, and we can achieve accuracy rates that were basically impossible with traditional approaches that can even beat human accuracy rates. And then series data. So one of the key things that Devin is actually using neural networks on is series data, which most people think of as time series data, but there are actually two other kinds of, well, I mean, there are lots of kinds of series data, but there are two kinds that I care about, right? One of them is textual data. So textual data actually is series, right? Sentences are an ordered set, right? So that becomes a series. So that's actually how Google Translate works, right? They use an artificial neural network behind the scenes that learns from textual series data. One network decodes it, learns basically what sentence structure should look like, and another re-encodes it in another language. It's two neural networks sort of layered on top of each other. What we at Devin use it for some is actual depth series data, right? So as you're moving down through the earth or over through the earth, that's also a form of a series, right? And so we look at depth logs, and we feed those into a kind of a neural network that's good at doing that kind of data. All right, so I said I'd come back to how they work. Let's drill into how they work. So I said neurons get connected, right? We build layers of neurons. Neurons get connected, and they learn by tuning the weights and by tuning the actual algorithm in the neuron. So at their simplest, ANNs take inputs, right? So x1, 2, and 3 would be 3 different features in my training set, right? I'd have 3 columns here, presumably tons of samples. I send that in, and the neuron, the artificial neural network actually has a matrix, a weights matrix, that says, how important are these relative features to me, right? One of these features may not be predictive at all, and so this weight matrix would get reduced over time to be infinitesimal. Basically ignore that. And so I take these weights, I sum it, and then I perform a function within the neuron itself also. So I say, I'm going to look at these weights, I'm going to aggregate them, which is why I tune the weights of each of them, right? And then I'm going to do something to that. Right? And there are a number of functions that we can have inside these neurons depending on the problem we're trying to solve. So at their simplest, they do that, right? And then we get the output. We get our hypothesis, right? And so the very first versions of these, the perceptrons, right? They just took these weights and they had what's called a linear threshold unit where it basically just goes over and it goes up, right? It's 0, it's 1. And if you cross a boundary, it instantly becomes 1, right? That's the simplest, right? It's a stepwise kind of function, an LTU. So again, an LTU basically is as simple as h equals 1 if the weighted sum of my x's is greater than or equal to 1, right? That's it. If it sums to greater than or equal to 1, I say, boom, my function makes it a 1 for my output. That's hard to train for some reasons that we'll talk about here in a minute, basically because it's not differentialable. There's no gradient, right? But we'll get back to that. So a more sophisticated example, right, an example that you might eventually actually use is this perceptron, which could categorize 3 different binary classes. So I have 3 different LTU outputs. Is it class 0, 1, or 2? And I kind of like that Python, right? So a perceptron, this could categorize into different binary classes. This example would output 3 classes. It's a multi-output classifier. So if I wanted to, in some of the image classification techniques, right, I would need 10,000 of these, right, because there are 10,000 different classes. So I need an LTU at my output layer for every class. And so you can see here, everything is connected to everything, right? My x1, 2, and 3 are connected to every one of these LTUs, right? And so that's how we make these what are called dense networks. The other thing that's new on this is this 1. This is actually our bias neuron, right? And so that basically just initializes them all with some constant, right? That just kind of acts as a constant input, right? And we have a bias neuron per layer because it helps us with training and regularization, basically. I know I'm going fast. I'm covering a lot of stuff, right? So if you have questions or you want me to cover something else again, I'm more than willing to stop and slow down. So we can stack these to an arbitrarily dense or deep network, right? So we can stack these layers of LTUs, right? We saw one where it was just one. We saw one where it was three. Now we're seeing them where we can add new layers. Each of these input and output layers are called hidden layers. So this is our input layer again, right? I've got 3 features. This is our hidden layer where you can see that we don't actually directly interact with it, right? And then we've got our output layer, and you can see everything is connected to everything, except they don't skip column, they don't skip rows, right? My input is not directly connected to my output. It has to go through the layer, but every layer is connected to every neuron in every other layer adjacent to it, right? And so these become very dense. So each one of these arrows is a weights in my matrix, right? Which means that my matrices get exponentially larger as I add more neurons and as across, right? Because it has to be connected to everything before and after it in those individual layers. And so eventually you start running into things like out of memory on your GPU, right? Which becomes one of your key constraints with doing this sort of training. And so sophisticated artificial neural networks, we develop very, very deep. Some of the leading artificial neural networks like Google's GoogleNet or some of their other classification, whenever you print it out, right, you need a plotter, right, because it's hundreds of layers connected in unique ways now, right, to discover new features, right, and to propagate that signal forward. Because we develop a more nuanced neural network as we add more layers functionally, and as we add more neurons. You have to have a balance of both of those. All right, so I talked a little bit about what they are. I talked a little bit about what they look like and how they work, and we talked about dense neural networks now. So what do you really do to train and prepare a neural network, right? First off, we have to prepare the data, and most folks say that that's the 80% of the work, right? We have to prepare it, we have to normalize it, and we have to shape it. So we have to make it a consistent matrix shape. So for example, we cannot use irregular images. You can't have one image that's 100 pixels by 100 pixels and another that's 28 by 28 whenever you feed that into your neural network. They have to be consistently sized, so you have to resize them. You have to make sure that your values are normalized generally between 0 and 1 as well, because of the way the weights work in the neural network. If you have some that are 255, but most are between 1 and 5, you will not have a very predictive network. So you have to use some regularization techniques, things like that. Then we build the network. We have to select an architecture. We talked about just the most basic one. Then we have to talk about our hyperparameters. And so ultimately, these are kind of the key things that we start balancing and working through. So we're going to talk about the neural network types. So dense, we already talked about dense, right? This is where I have layers of neurons that take my input, and all the layers are connected to everything in the layers above them and below them, right? And so this is a fairly simple artificial neural network. It's pretty good for general purpose problems. But if you start doing things like images, you quickly realize that you cannot make a sufficiently predictive network out of this because you rapidly run out of memory. Right? Like I said, those matrices get exponentially larger as you stack them. Images tend to be pretty large, right, relative to your tabular data. And so we have a lot more data that we're trying to propagate through our matrices. It doesn't work. We have to kind of reduce our resolution every so often. So we have another neural network type for that called a convolutional neural network, which we'll drill into here in a slide or two. This type of neural network is specifically designed for image recognition type tasks. And it could actually do feature recognition and whatever, right? We're experimenting, some companies are experimenting with convolutional neural networks on seismic data, right? Because it's a multidimensional data set that isn't exactly image data, but it is in a fairly predictable format, right? Where we can identify subsurface features. So you can apply the same kind of principle to that. Recurrent neural network is for that series data. So that's the kind of network that we would use for depth series data, because it has the concept of state through time or through whatever your series is, right? So for us, it'd be depth. And then adversarial is one that is an unsupervised type network that encode and decode to model the key features of the input. So this is a great way to kind of pre-train a network. If you don't have a ton of training data and you sort of want to identify the key features, you can use an adversarial network to do some pre-training and then kind of hook another network on the other side of it and benefit from that. All right, so convolutional neural networks. These are modeled on the architecture of the visual cortex. So vision is made up of overlapping receptive fields which together form an image. This is realized as a convolutional network. So here we basically are saying if I have this image, right, and this is my image space, we're actually aggregating up, right? We're looking at a definable window across this image. And we basically take this window, right, and we move it stepwise across the image in all directions. And we can configure how this gets moved across, right? You can say it runs in a sliding fashion, or you can say it runs in a non-overlapping fashion. You can customize this to your use case. But at the end of the day, it forms almost a pyramid of data, right? Where we look at the entire image space and we aggregate it here. And then we look at this image space and we aggregate it up. And so fundamentally what these look for are things like, I've got a picture, there's a car in it, but the car could be at any part of the picture, right? And it's presumably not at the same part of any other picture that we're trying to identify. So I want to find cars in all my pictures. And so what this does is it aggregates up this image space, is it looks for the similar signals all across our image, right? And it kind of moves it up the stack. And if you train it to look for cars, it'll look across this entire image space and it'll try to find the basic features, right? So usually with very deep convolutional neural networks, the initial layers actually just identify basic shapes like circles, lines, squares, right? And then the higher order layers start to aggregate those basic shapes that have been identified in the image into a discernible object, right? And I'm explaining all this, but at the end of the day, whenever you train these networks, you actually kind of find what works, and you don't really have to understand the linear algebra. We'll look at the code, and we're not calculating matrices weights, right? And to be honest, these become very much a black box after you've trained them, where if your business said, well, why did it do this instead of this? It's pretty much impossible to reverse engineer that back out of these, especially fairly sophisticated ones, right? You can experiment to find out what the architectures are that best meet your needs or your use case, but you very much not in the same, you can't, like in a linear regression algorithm, right? Say, well, this is the relative weight for each of my features. It really doesn't work like that, right? You can look at the matrix weights, but it's very difficult to reverse engineer that back into anything intelligible. So anyway, I say that to say, this is all kind of context that helps you understand why you would do what you would do. But at the end of the day, to solve business problems, you don't have to have a deep and intimate understanding of kind of the math behind these, which obviously I'm not covering anyway. Anyway, so you can see that this, in practice, really would not be a dense, fully connected network because I'm not connecting these cells, right, to the layer up here, right? It only has a portion that gets sort of aggregated up a stovepipe of data, if that makes sense, right? And so my matrices become smaller and smaller, well, not really smaller and smaller because I add more and more sorts of layers of inference, but the image itself would actually become smaller and smaller, and we usually shrink that. And we'll actually see an example of a convolutional neural network here in a minute. Well, in a few minutes. So recurrent neural networks. So these are my favorite because they help me solve the most problems. So these networks maintain state across time steps or across whatever our sort of horizon is, right? Allowing them to recognize patterns in sequential data. That's the key, right? And so we saw ordinary neurons, right, where they just kind of took an input or a set of inputs, and then they gave us an output or connected to another layer. These neurons are fundamentally different in that they're actually more sophisticated inside, that they connect to themselves over time. And so this is actually what it looks like instantiated, right? Where I have my input, and then it gives an output, but it also gives me sort of this recurring weight or this recurring signal back on itself. So unrolled, this is what it looks like. This is what this one neuron looks like, where this one neuron says, I'm looking at X for time step 1, time step 2, time step 3, and I'm going to send the signal, I'm going to send some signal that is trainable in and of itself forward across the time steps. And so I'm not actually sending X1 forward. I'm sending a matrix that I've derived using calculations in this neuron forward that I think, that this network thinks, is sort of the important signal or the important information that would help me identify a time series, basically, right? That would help me identify what happened before me because I think it's relative to what's going to happen after. And this can be propagated an arbitrarily long distance in the future, right? It doesn't have to be this sort of facile thing where the X3 has no idea what happened in X1. There's actually a signal that's propagated as far as actually makes sense. That's trainable. So the neural network learns how far do I propagate which parts of the signal over time steps. And I say time steps, but you should always think just more of the series, right? So by unrolling the network through time, they can be trained via backpropagation through time, which tunes the time step weights along other connections. So backpropagation, I think I talk about, so I'll come back to it. So I'm not going to dwell on that yet, but that's just how networks are trained. So this is an example. If we looked at the other slide, right, each of these neurons, we're just drilling into and seeing that there's a lot of machinery within each of them. So we've just drilled into one neuron. And so GRU cells are the most sort of prevalent, state-of-the-art recurrent neural networks, and they're simplified LSTM cells. So LSTM are much more complicated. You'd see a lot more on this diagram. What has been shown is that GRU cells are just as effective for most tasks and train significantly faster. They maintain state using hidden propagation value. One gate manages hidden state, and the other manages how it goes in. So here's what happens. So we get this time step, right? So we saw how they talk to each other across, right, across time. We're getting the time step to come into this cell, and it actually goes down here, and it goes through these functions. And one of these functions controls what part of my hypothesis is influenced by the time step. And the other one dictates, do I overwrite my memory with this new time step? Because I have to do both of those, right? I want to alter the signal that I'm getting forward, and at the same time, I want to govern how that signal gets applied to my hypothesis. And so I have two functions for that, and then I have another function that actually does the integration between my x value, which is, you know, my matrix coming in, and the previous time step. And so that's really kind of the meat of this, right? And the different color coding indicates different activation functions. I think the two FCs are these two are a TANH, and this one is a sigmoid activation, which we'll talk about a little bit, but that's further down in the weeds than you would need to go. But at the end of the day, what you do is you import your GRU cells and you use them on a time series, right? And so you don't actually have to understand all the magic that works in the box. You just have to know that there is some. And so what I have found for these is that a dense neural network, even one with exponentially more, 10 times more neurons and twice as many layers as I'm using a GRU, the dense is significantly less predictive of things that are properly time series, right? And so if you look at, I actually think I have an example of the training output of that I'll show, and then I'll come back to, because I know I keep saying I'll come back to stuff. So this is TensorBoard, and we'll talk about this here in a minute. But this right here is a dense neural network on the same data set on my validation data. So you can see it never really gets better, right? It starts out here, and then it just bounces around, right? So I'm obviously not really getting anywhere. But these are my recurrent neural networks where you can see a consistent and more stately decline, right? And even on the training data set, these are my dense networks up here, and these are my recurrent networks. And the value that I'm mapping here is the loss function, or the mean average, mean squared error. And so lower is better, right? And so you can see I'm training these, and the longest ones went for about 2 days, right? And so you can see I'm training them, and my mean squared error is just getting lower over time, right? And if you can see all of my validation data down there, you would see it doing something similar, but it doesn't get quite as low because these obviously overfit just a little bit. But we're still significantly more predictive than anything we could do traditionally. Okay, so I said I'd get back to training models, backpropagation, all that good stuff. Training models with deep neural networks is fundamentally an optimization problem. So I actually just talked about mean squared error. Fundamentally, what we're trying to do is we're taking the data set, we're taking the predictor, right, and we're just trying to get closer, right? And so we optimize the weights and the neuron function in order to model the input, right? And so conceptually, we can say this is my input space, right? And I start, and my problem is not very accurate at all, or my model is not very accurate, so it starts all the way up here, right? This is my mean squared error, and it's very large, right? As I tune my matrix weights, I actually do this what's called gradient descent down into my optimum solution, which obviously this plot would look different for everything, but what you're trying to do is you're trying to find a global minimum. And what this demonstrates is depending on where you start, if you're using something like stochastic gradient descent, you can find local minimums and get stuck there too, right? And so you can see it kind of bounces around, but eventually you find your minimum. And you can use some different techniques to try to get out of local minima and things like that. But the kind of the core concept is we have this problem space, and all that we're doing with neural networks is trying to find the optimum, right? And so we have functions in our neural network that just spend their time saying, okay, I'm going to tune down the gradient, right? I'm going to move down the gradient in this 3D space to try to find a lower, basically to get as low as I can, right? To just keep moving down the gradient, tuning the weights down that gradient until I reach the optima. So training models. So neural networks are provided training instances, the connection weights that would produce a correct output are strengthened. So what it does is it goes through and it starts out and it calculates the answer, right? We just randomly initialize all the weights with just random numbers, right? There are different distributions that you use depending on your problem. There are different numeric distributions that have been shown to work. But at the end of the day, it's just random numbers, right? And the very first time, we just send our features through and we see what is the prediction that we get out, right? And of course, at the beginning, it's wrong because it's all random, right? And so we look at that gradient space I just showed. We start out near the top and we say, which direction would get us closer to a right answer? And we start at the top of our network and we tune the weights all going backwards, right? And so we calculate the answer and then we go backwards to say, I'm going to tune each of these neuron functions, right? To get closer to the right answer. And then I'm going to tune all the weights going to that neuron to get to the right answer. And so on down the network, right? We drill from the top down, all the way back to the bottom layer, all the way back to the weights for our features. And then we just do that over and over and over, walking down that gradient. Training deep networks presents a unique challenge because weights must be adjusted in each layer according to their contribution to the output. This is solved with the backpropagation I talked about. So at the end of the day, we have thousands of neurons in potentially hundreds of layers. How do we figure out what this neuron's contribution is? And that's why we work from the top down, right? Backpropagation works from the output backwards through the network, evaluating each weight and its contribution to the gap between the prediction and the ground truth, adjusting it accordingly layer by layer. Sorry, I already explained that. All right, activation functions. So I talked a little bit about LTUs, which are not up here because nobody uses them. The real ones that we're interested in are sigmoid, which gets used for usually kind of classification tasks. I want it to be a 0 or 1. I usually use something like sigmoid. Hyperbolic tangent, we don't use that much. ReLU is the most used. And I'll talk about these in a minute. So these functions, threshold functions like LTU, are hard to train because there's no gradient, right? I said it was a step function where it literally goes like that, right? There's just a step. You cross the threshold, it goes from 0 to 1. There's no gradient. So how does the model learn, all right, I'm close. I need to move just an inch to the left, right, to get the right answer? It has no idea because it's completely binary. Right? With these, it can say, all right, I predicted all the way up here, but I wanted to be halfway down. I know what the gradient is, so I know that I need to tune my weights accordingly, right? And so these are differentiable at everywhere except 0 in this one, right? And so I know how to train these. I know how to get a gradient of these. I know how to calculate against them. So sigmoid functions, they're great because they provide a non-zero derivative everywhere, which is, again, how I train, right? I'm interested in the derivative. I'm interested in the gradient. Linear functions like ReLU, it's continuous but not differentiable at 0, but it's commonly used because it's much faster than sigmoid to compute. You can see this is a predominantly linear function, right? So whenever I'm calculating this literally millions and millions and millions of times during training, the speed difference between this and these two becomes appreciable. And so ReLU is usually used because the fact that it's not differentiable at 0 tends to be more or less an academic concern. So why do we care about activation functions? These are actually the functions that we end up putting in those neurons. I said that there was a function in those neurons. Whenever we're coding, we actually say, I want to use a ReLU function or I want to use a sigmoid function in those neurons, and this is the function that gets applied against the weights that come in. All right, so TensorFlow. So TensorFlow is the dominant product in this space. So Google came out and they basically said, we have an internal deep learning framework that's proprietary that we're not sharing with anybody, and that was an earlier generation. Since then, they've built this subsequent generation in TensorFlow, which is a Python front end with a C++ back end, and it allows you to instantiate all these neural networks that we've been talking about. So TensorFlow is one of the newest frameworks, but it's the most popular framework because it has Google's explicit backing. They say it's the tool they use internally, and they are supporting it and actively contributing to it. It is open source, and it has taken off wildly. And we'll talk a little bit about the good and the bad of TensorFlow. But what it does is it's built on the concept of an execution graph, or a DAG, right? All your operations populate the graph, which TensorFlow optimizes and executes at runtime. So if you're familiar with Spark, you understand the concept of an execution graph. This is the same thing. You come in, you put all your operations in, and it's not till you actually run your training here that it executes your graph. So the entire thing is like Spark with lazy execution, right? You go in, you put your operators in, and then you tell it what to do, and then it optimizes the full graph, right? Because it knows everything you're trying to do, because you've pre-populated that, and it can do that, and it can batch it and do some of that other stuff. So why tensor objects are passed between the operations and the graph, hence TensorFlow. Tensors are matrices. Tensors are multidimensional matrices. Here, it's a sort of a proper noun for an object that's in TensorFlow, but it's just named that because matrices are passed between the operators in the graph. So tensors are objects in the Python API that are the result of an operation in the graph. Operations produce tensors, TensorFlow. Tensor is a mathematical term for an n-dimensional array, right? And so that kind of makes it a little confusing whenever you're talking to folks about TensorFlow, because you've got a lowercase tensor, right, that's a mathematical term, and you've got an uppercase tensor that's actually a Python API object. But that's kind of how they relate and why it's called what it is. All right, so TensorFlow has a bunch of APIs. We'll actually see an example of the fact that it has a ton of APIs. It has a base API. So whenever it came out, that's all it had, right? So you could do linear algebra with it, which was great, except it's very verbose. And people don't want to adopt Python to do deep learning with a verbose base API where they're doing their own matrix multiplication, right? You don't want to do that. And so additional sort of facades have been built on this base API, including TF-contrib, TF-slim, and Keras. And Keras is actually built on top of these substrates, right? But TF-slim isn't necessarily, so I wouldn't consider this a physical diagram. It's more a logical of, I can use the base API to do extremely low-level operations. I can use TF-contrib to do more moderate operations. And then Keras and TF-slim provide really, really high-level wrappers, right? The highest level wrappers that are currently available. So Keras is great because it makes it really easy. We'll see an example of some TensorFlow code versus some Keras code, and TensorFlow is much more verbose, right? So data scientists love Keras because it's pretty much intuitive. You don't actually have to know any of the stuff that I've told you except to know how to select the different matrix type, right? You'd still have to understand the difference between convolution and a recurrent to know which you should choose, but then you don't have to understand how they work to get them to work in Keras. So we'll see an example of MNIST and Keras. MNIST is a very famous data set consisting of handwritten digits. It has 60,000 training examples and 10,000 something test examples and validation. Each example has a label assigned, so it's a supervised data set. And each image is a grayscale and 28 by 28 pixels. And so this is what they look like whenever you zoom them in. It's an old data set, it's been around for a long time, so there's a lot of academic research around MNIST. And it's a prepackaged data set in most machine learning libraries, including sklearn and including TensorFlow. So I'm not showing you any of the pre-processing because we're not here to code. But I'm showing you what it looks like whenever you do it. So I've talked about all this stuff, right? But what does it really look like? And so in Keras, you actually come up here and you just instantiate a sequential model. And all a sequential model means is I'm going to do these add operations, and it's just going to build it iteratively from the bottom to the top, right? So this very first operation builds the bottom layer of my network. And I'm just adding layers as I go up with these commands. And so this is it. This is building a model in Keras. That's all it takes to build an MNIST model, right? I've still had to pre-process the data, which could or could not be trivial depending on your problem, but the model creation is not that hard. Even the sophisticated models I've built are still only, 30 lines of code maybe, right? And so what I've done here is I've added a convolutional layer, so convolutional 2D, because these are two-dimensional, right? They're images. I've said my kernel size. I showed you that footprint thing that moved along the image, right? That's my kernel size. So I'm doing 3 by 3, 3 pixels by 3 pixels. That's kind of been shown to be, it's better to add more layers with 3 pixels than to make a bigger footprint. There's some Google white papers out there on that. There's my activation. I showed you ReLU, right? Different, it looks like that. And then input shape is just the shape of my input data. In this case, it's 28 by 28, right? That's the pixel footprint of my data. Now I'm adding another layer on top of that. So that 32 means that I have 32 neurons stacked in this layer looking for features. That's all they're doing. They're trying to filter it to look for the lines, to look for the circles that I told you about, right? The more the better, but the more also makes my matrix much larger. So I can't make one that's 500, right? I'll run out of memory space. So I have to add more layers instead. So now I'm adding another one that's even deeper, right? It's 64. It's looking at a 3 by 3 space, and it's doing ReLU. Now I'm max pooling. What max pool does is it reduces the size of the image. It basically says take a 2 by 2 space, take 4 pixels, right? Turn them into 1. now that you've done some of this pre-processing. So it shrinks my image by half in each side, in each way. And then I'm doing dropout, which regularizes my network. Dropout's kind of a thing that you wouldn't think would work, but it does. It actually takes half of the neurons and it just drops them out of every training example. Or in this case, sorry, it's 25% of the neurons. And that's all it's really doing. So you saw those dense layers, right? This is just taking 25% out of every layer and just saying, don't use it for this one, right? It doesn't exist. What that does is it regularizes your model. It keeps it from overfitting. I'm flattening it, which takes it from a 2x2 matrix into just one long matrix. I'm putting 128 of those densely connected neurons on it. I'm using dropout there. I'm trying to predict 10 different things. So at the top, I have 10 neurons, like I showed you earlier, right? With softmax, because I'm trying to predict categories. I'm compiling my model, and then I'm training my model, right? And so there's some different cool things that you can do in here and in here. But at the end of the day, that's what I'm doing, right? I'm building my model, I compile it, and I train it. That's Keras. I know. You're not going to be an expert out of Keras on this, right? I'm just giving you kind of a taste of it. This is how you do that in TensorFlow. And this doesn't even include the model compilation or the training, right? And so you can see here, I'm not going to walk through all this in the same way that I did, but what I want you to get out of this is up there under TF name scope conv1, I have to declare my matrix, I have to declare my bias, and then I have to declare the shape that uses that matrix. I didn't have to do any of that, right? I'm also using these scopes to variable scope my data. I didn't have to do that either, right? So you see I have to do a lot more work in TensorFlow. Now you get some nice things out of this in that you get much more control over the model. You can do lower level operations here and you can do multi-GPU training, but you see the verbosity cost that comes with it. The other interesting thing that you should note is TensorFlow has a lot of ways to construct these layers. You can do TF contrib Keras layers, you can do TF layers, and you can do TF layers. And you can see these are all convolution 2D objects, right? So you have to choose your API based on what you want to do. So it can be a little bit non-trivial to say, even in TensorFlow, right, which API do I pick? Because there's kind of a proliferation of APIs now, right? All right, TensorBoard. I already showed you this a little bit, but I'm coming back to it because I want to talk about it. How do you see your model's performance, right? So I said that these long ones that are 200 epochs took 2 days to train. Well, I don't just want to be sitting there for 2 days and assuming it's getting better, but uncertain, right? And so you can come in TensorBoard and it gives you a real-time view of how your model is progressing along whatever metric you set, right? So this metric is mean absolute error, mean squared error. For my training data and for my validation data. And it plots this all out for all of them. So I can compare my models against all my other runs. And I can see, and you can see some of them I didn't run for very long, right? Some I was doing tests on, some I ran for 100 epochs, some I ran for the full 200. You can see this one I actually loaded weights from a previous run to continue training it. So TensorBoard is very flexible and all it really does is plot your scalars or your data and kind of give you a view into how your models are performing. All right, and then I got one more slide. All right, so challenges. What are the challenges? So, I mean, the first challenge is obviously skilling, to be honest, right? If you think about the three, people, process, technology, right? The technology is there. It's the people that's a challenge right now. And so getting folks comfortable with it, getting the skills there to support it, to operationalize these models, to continue running them, it's still a challenge, to be honest, right? And we're chewing on that and working through that at Devon with trying to get other folks empowered and using it. But I think that's probably going to be the first challenge that I don't articulate here. These are all technical challenges, but that's almost always the first challenge. So the technical challenges are vanishing and exploding gradients that we didn't talk about too much. So neurons can actually die because they get stuck infinitely close to 0 or to 1 on either end of like that softmax that you saw, right? And so if they get infinitely close to 0, there's no realistic gradient adjustment to bring them back. So we use ReLU and we use small training steps to solve that, but eventually in really, really deep networks, that can still become a problem, right, over time where a large number of your neurons can quote unquote die, right, where they just become not predictive dead weight, which makes your model very limited. Exploring the hyperparameter space. So I talked about all these different things you can do, right? You can use different activation functions. You can use a different number of layers. You can use a different number of neurons in each layer. You can use different types of neurons. You can use different training options. You can use different training parameters. That's all the hyperparameter space. Those are all the parameters for your model. How do you find the optimum set? It's almost impossible, right? Because if a model takes 2 days to train and I can have an almost infinite amount of variation in that, it's impossible for me to truly find the optimum, right? And so there are some different strategies for that, but at the end of the day, you almost just have to experiment and then hone in on your successful experiments, right? Scaling networks across GPUs. So I talked about this is all a matrix, and it's all stored in memory, but it's all stored in your GPU's memory. And so at the end of the day, especially with convolutional neural networks, we run out of memory consistently, right? And so the big players scale across GPUs, but that slows your model training time exponentially, right? Because if you think about how fast the memory bus is on a GPU, there's no way to replicate that across GPUs, even in the same system, much less across different systems. And that's just a fact of life. The other challenge too is Keras does not actually support multi-GPU training for the same model. It'll support speeding your model up with multiple GPUs, but not sharing the weights across them to make your model more robust. So you have to use TensorFlow today. Supposedly they're working on it. And then optimizing your network. So Keras specifically does not produce optimized TensorFlow code. It uses the reference implementations, which ironically for TensorFlow are not optimal implementations in many cases. And so if you care about speed, if your model takes days to train, you actually have to find the primers for optimizing TensorFlow, which will show you how to recode the stuff that you've done to use their more optimum approaches with their APIs. So that's kind of a pain, to be honest, right? We haven't actually run into that problem because for us, the developer speed is more important than the model training speed, right? For us, we'd rather the developers kick the stuff out faster and just let the machines chew on it for longer instead of having them spend forever optimizing them. For our training, by the way, we use the Azure In series, which are GPU enabled. They're actually identical in hardware, to my knowledge, to Amazon's GPU enabled, and they use K80s from NVIDIA, and they're very competent. They do what they're supposed to do. They have 11 gigs and 1 core. So we have had good success with that. Yeah, meets our needs. All right, so that was a whirlwind tour of a lot of stuff. Any questions? All right. Yeah. Yeah. So I can talk about a few of them at a high level, right? So we're currently applying neural networks to seismic data to try to understand seismic data to extract features from it, because seismic data is actually several terabytes from a shoot. And so right now you use vendors, you send the vendor your seismic data, they sort of extract it and they do what's called post-stack. We're trying to do some post-stack work ourselves with neural networks. Can't talk a lot more about it other than that. The other very interesting thing is trying to infer well attributes. So you go out to the field, you don't run the same tools down every well for cost reasons. So we're trying to infer well attributes from existing wells that we did do that for. And we can use neural networks for that. Image classification, so one is like document classification. There are tools out there for that, but we turn PDFs into image files, and then we do classification because we have a gigantic training set, but we have these network drives where people have just thrown everything out there, so we're writing our own models, our own convolutional models to basically say, hey, what kind of documents are we finding out on people's network drives and things like that, you know, and classifying them all. Yeah. Any other questions? Yeah.
So I've heard that things like captchas on the internet, like proving out a level have two different captchas. One's going to be a one that everybody knows the answer to. One's going to be we don't know the answer.
Yeah.
Without human beings type in,
Yeah.
the machine will learn. Now they selling that. You know if they're selling that data to somebody else or
Yeah.
that themselves?
So the question is are captchas generating training data for machine learning? So I'm not working in that industry, but my understanding of it is yes. So there are actual companies that provide that as a service, and I think the business models vary, but in some cases they provide the captcha service for free because they get to harvest the data and either train better neural networks or to sell the labeled data to other companies. I think it broadly depends. To be honest, though, a lot of the most sophisticated companies like Google don't really need that anymore, right? They get all the labeled data for free, and their neural networks are more sophisticated than really kind of need that input. Microsoft's probably in the same boat, right? But overall, that kind of comes back to data as the new oil, right? Where labeled data training sets are extremely valuable.
That was my follow-up was, is it sometimes very difficult, if not impossible, to get good data sets?
Yeah. Yeah. I would say, so yes, it's very difficult to get labeled data sets in almost any industry, in almost any field, because they tend to be the most expensive thing to generate by hand. In some cases, we get them for free with our historical data, right? Like if we're trying to predict rig states, we have years worth of rig states, right? But for some of your other things like equipment failures, right? We don't always track equipment failures in the same system that has the telemetry data for the equipment, right? So I don't have labeled data there unless if I have somebody go merge those two, right? So that becomes very expensive and time consuming. So yes, training data is almost always the hardest thing to get. Yeah. What was the question? Yeah. Yeah. So preparing the data, there are a number of tools to help our sort of citizens prepare it. But most of all, yeah, so data prep can be challenging. In a lot of cases, we actually just have to have folks go and kind of munch the data and merge it. Like for one of our things that we're doing in Canada, it has taken months for them to just key the data together, right, to prepare it. And so on that front, it's actually the same problem we just discussed, right? But once that minimum amount of preparation is done, there's some really good SK learning libraries to do the scaling and to do the imputation. Those are predominantly what I use. The challenge kind of tends to be finding what are the right dimensions for my data to go into my model, which becomes another form of a hyperparameter, right? How much time series do I use for a current neural network? How large do I scale my images to, right, whenever I put it into a convolutional neural network? And then kind of how do I manage those repositories? Netflix had an interesting talk on that where they talked about that they actually have systems that generate test and sort of sanity checks for their models and for their machine learning that's a governed subset of their data universe. Because the other converse side of that is sometimes we have too much data, right, to run through the model in a timely fashion, and we just want to do some sanity checking. That's actually a non-trivial problem too. So I don't know if I totally answered it, but that's the answer I got. Yeah. Yeah, so we do some neural networks in SAS, so we're a big SAS shop, but SAS is very limited. It does 5 layers, 100 neurons per layer to my knowledge, and that's it. That's a small network, and it doesn't do any of the other kinds that we talked about. It only does dense, right? And so that is very limited in its predictive power. Won't help you on images, won't help you on time series data, right? It's very limited. We use MLlib and Hadoop. And we use it predominantly, though, not for neural networks. We predominantly use it for smaller data sets or sort of more traditional problems that we would do like a random forest on or something like that, right? And so we still find it very successful for that. And we still have problems that we run through that exact scenario. Because if we don't have enough data, it doesn't make any sense to put a neural network on it, right? We'll just end up regularizing out all of the advantage of it, right? And just kind of going through the trouble for nothing. So we actually do not use those solutions for neural networks predominantly. We use those for sort of traditional machine learning, what I'd consider traditional machine learning, and then we use TensorFlow for neural networks where we say, hey, we've got a sufficient amount of data and those approaches have not been sufficiently predictive, right? Or they just can't do it, like with the pre-stack stuff that I was talking about where it's terabytes, we just can't really put that in our traditional systems effectively and expect to get anything out of it. So, yeah. Yeah, so how does it handle online learning? So online. So we do not do online training. I don't know that you'd exactly be able to do that easily. What is very powerful about TensorFlow, though, is they have a solution called tensor serving, which is used to actually host your models in an online fashion, right? And so you can do real-time predictions. It presents a REST endpoint, where you can submit whatever your matrix size is, right? You obviously have to pre-process the data through a function before that. And then it'll give you the response, whether that ends up being a really small batch or a really large one. It's up to you and your model, right? But tensor serving is very powerful because it actually just continuously pulls the file system, and it in real time will upversion your models, right? And so I think LinkedIn modified it to run directly on S3, and so you can basically just put your new model in an S3 bucket, and it'll just keep pulling that S3 bucket, and just suck in your new model and seamlessly, right, update the model, right? And so obviously if you versioned the endpoint, you'd probably want to do it differently, but if you're just updating your weights, it makes it fairly trivial to update your model for your customers. So tensor serving is very powerful for that. Yeah.
You said that TensorFlow is open source. Is the surrounding ecosystem also open source, like TensorBoard that you showed?
Yes. Yes. So TensorFlow is open source. TensorBoard is open source. Keras is open source. All of the solutions that we are using are open source in this ecosystem. So yes. Yeah.
What's the license?
The license?
Yeah, what license is
I don't know. I think, I don't know, actually. Maybe MIT. I'm not sure that it's Apache. That's a good question. Any other questions? All right. Going once, going twice. All right, thanks, everybody.